Okay, so as in the last video, we have discussed about the charges Q1, Q2, Q3, because we have already discussed, right? In parallel, the charges which will be stored by the capacitors would be different. However, same potential difference would be provided to each member of the capacitor, right? While in series we discussed that charge stored by the capacitors would be same, however there would be different potential difference, but in the parallel there would be different, but there would be same potential difference, however there would be different charges, right? In the last to last video we discussed about the definition of the parallel combination or capacitors in parallel. We actually get to know that what it is, right? We got to know that when two or more capacitors, which means when three capacitors are connected in such a way, the positive and the positive terminal of a battery is connected to one and common point, right? This positive terminal of the battery is connected with the one common end point, right? And an other end of each capacitor is connected with this common point, and this common point is connected to the negative terminal of the battery, right? This such combination is what we call the parallel combination or capacitors in parallel, right? Then we considered our equation, right? We considered three capacitors C1, C2, C3, right, which were connected in parallel across positive and negative terminal of the battery of potential difference provided V volt, right? Each plate of the capacitor stores different charges as Q1, Q2, Q3, however same potential difference provided to each of the capacitor, right? So we then wrote our general equation in which we were known that charge stored on the plate of the capacitor would be directly proportional to the potential difference provided to it, right? So when we remove this proportionality sign, we got is equal to C. So Q is equal to CV, where we know that C is the capacitance of a capacitor, right? So if we are finding, we know that charges would be different on the each plate of the capacitor when they are connected in the parallel. So right, if I want to find the charges on the first capacitor, so Q1 is equal to C1. Since same potential difference would be provided to each capacitor, that's why V, right? So Q2 is equal to C2V. Again, Q3 is equal to C3V, right? In today's video, we're going to discuss, right, what the total charge would be equal to, which would be stored on the plate of the capacitor, right? So let me write here the total charge stored on plate of the capacitor is right. Wait, let me highlight this point. The total charge stored on the plate of the capacitor would be equal to Qt, right, which is the total charge, is equal to Q1 plus Q2 plus Q3, right? This would gonna give us the total charge which would be stored on the capacitor, right? If we replace these all capacitors by a single capacitor, right? Now we have a definition here. Consider this equation as equation number 1. Equation 1, right? Equation 1. Now, if we replace these capacitors by a single capacitor, this would be known as equivalent capacitor, right? Called equivalent capacitor, which would be denoted by CE, right? As we discussed this in the series combination as well, which acquire same potential and store same charge on the plate of the capacitor, right? Acquire same potential and store same charges on a plate of the capacitor, right? So now Q would be equal to CV, CE, which means equivalent capacitor into V, right? This would be our final equation. Now we're gonna find the equivalent capacitance, what that will be equal to in the parallel combination, right? Now putting Q1, Q2 and Q3 value, right? Initially we are using equation number 1 and we know that our equation, this is basically QT, right? QT equal to Q1 plus Q2 plus Q3, right? This we already know when we need to find the total charges on the plate, right? So QT is equal to CE into V, right? Q1 we have already found, that is C1 into V plus Q2 is equal to C2 into V. So here we have C2 into V plus Q3 is equal to C3 into V, right? Now see what is, common here, right? So CEV is equal to, we have V common in each, right? So V would be common in bracket C1 plus C2 plus C3, right? V cancel with this V. Sorry, I have cancelled CE. So this V cancelled with this V. Thus the remaining is CE is equal to C1 plus C2 plus C3, right? So we got our equivalent capacitance. What that would be equal to in the parallel? That would be equal to basically the sum of individual capacitance, right? In series we had the reciprocal of equivalent capacitance is equal to the sum of individual reciprocal of the capacitance, right? Here this equivalent capacitance simply will be equal to sum of individual capacitance, right? So now what this equation shows basically, let's write that. This equation shows that the sum, not sum, however, equivalent capacitance, equivalent capacitance is equal to sum of individual capacitors when they are connected in parallel. Connected in parallel, right? And this combination is also used in the circuits where the high capacitance is required, because equivalent capacitance store here energy, right? That's why it is used where the high capacitance is required. So this was all for today. In today's video we completed our parallel combination as well, or capacitors in parallel. We already completed our series combination or capacitors in series. Today we completed our parallel combination or capacitors in parallel as well.